white blood cells. Here's a lymphocyte. That's kind of an atypical lymphocyte with a lumpy nucleus. Usually that's a very solid cell. And maybe you saw some of these tiny little purple dots in there, which are platelets. It's a monocyte with that bilobe nucleus. And like I was telling you, most of the time when you see a monocyte, that nucleus is a lot paler than the other nuclei. Okay. Erythrocytes. So, red blood cells. They're chock full of hemoglobin. On average, 250 million molecules of hemoglobin in every erythrocyte. And the function of hemoglobin is to carry dissolved gases, carbon dioxide and oxygen. Showing you the size of a red blood cell. Generally, they're considered to be less than 10 microns across. That's some kind of rule of thumb you can remember. About 10 micrometers across. Your smallest capillaries will be half that size, which means if you get through some of the small capillaries, your red blood cells have to fold in half. Okay. And you notice they're biconcave, which even in the scopes today, you could probably see that a little bit. They're a little lighter and thinner in the middle than they are on the edges. Remember why I said that they're biconcave? Does that do
the capillaries?
What's that? No, not so they can fit through the capillaries. They have to be flexible for that. Diffusion, right. By being biconcave like that, they ensure that they're very thin and the gas can diffuse through them readily. Okay. That's why we think that they're biconcave. A few of the things that we mentioned last time. Red blood cells have no mitochondria, so they don't use up the oxygen that they're transporting. So they produce their ATP by glycolysis. And when we measure the relative amount of hemoglobin we have in an individual, we call that the hematocrit, or the iron count. And for males, it's above 13 to 18, a little bit lower for females, 12 to 16 grams per 100 mil. I will never ask you those numbers on a test, but many of you are going to go into clinical rotations, and this is a clinical reference point that you'll be expected to learn. So if you want to tuck it in there now, it might serve you well in the future. Okay. What I'd expect you to know is that if these numbers are abnormally low, that's a sign of anemia, okay? Because iron is the main constituent of your hematocrit, and so if your iron levels are low, your hematocrit is low, and that's a sign of anemia. Okay. I think we got as far as going through this picture before, right? We went through the globin and we talked about the fact that the globin chains, of which there are alpha and beta, two alpha and beta, they fold and they make this quaternary structure. It has the organic molecule. It's a folded lipid here. It's called porphyrin, makes a ring, and in the center of that is the iron. And the iron is the catalytic core of the hemoglobin. And iron binds to what? What's it essential for binding?
Iron.
Iron binds to oxygen. Okay. The oxygen literally binds to the iron. So without that, you'll have hemoglobin, but it'll be non-functional hemoglobin. And there's a type of anemia that deals with that. Well, you have two types. You have iron deficiency anemia, and you have something called pernicious anemia. Iron deficiency anemia, which we have a slide of, but I didn't put it out. In iron deficiency anemia, you're not able to make the porphyrin ring, you're not able to make the heme center, and the red blood cells just, they look funny. They get all swollen and pale, and they don't have hemoglobin in them, at least not functional hemoglobin. So they look weird. They look like big basketballs instead of biconcave. And in pernicious anemia, you lack vitamin B12, and that's necessary for folate synthesis. Again, I don't care that you remember this, but that's a necessary step in forming the globin chains. So if you're low on vitamin B12, you have what's called pernicious anemia, and then you don't form red blood cells properly. They wind up being very, very tiny. It's also sometimes called microcytic anemia. So it just changes the way your peripheral blood smear looks. And of course, in both of those cases, whether it's pernicious anemia or iron deficiency anemia, you don't have enough functional red blood cells, so it reduces the oxygen carrying capacity of the blood. And that's the money line for all anemias. Any anemia that affects your red blood cells reduces the oxygen carrying capacity of your blood. We went over the three types of hemoglobin. Oxyhemoglobin is when it's bound to oxygen. Deoxyhemoglobin is when it's not bound to oxygen. And once we form deoxyhemoglobin, it actually has a higher affinity for carbon dioxide. So in that case, it's more likely to bind carbon dioxide. And then we form carbaminohemoglobin.
What's the color of carbon?
Well, it's an interesting question. She has, what's the color of carbaminohemoglobin? It's actually a deep red. Okay.
So the same as the deoxyhemoglobin?
That's a good question. I've never read anything, I've never observed anything, the difference in color between deoxyhemoglobin and carbaminohemoglobin. I don't know. I think they're both a deep red, but I'm not really 100% sure about that one. I don't know if I mentioned this before in class, but in all of our models, deoxygenated blood is always shown as blue, right? And our oxygenated blood is always shown as red. And that comes from, you look at the veins and you see the blue ones in here, and those are veins. So we say, hey, it must be blue. It turns out that's not quite the case. Deoxygenated blood is deep red. It's a dark scarlet red, whereas oxygenated blood's a little bit brighter red. But generally speaking, veins run deeper than arteries, okay? So when the light comes in, it's filtered out. And when it bounces off the blood and comes back, it makes it look blue. It's not actually blue. It's an optical illusion created by the filtering of the light rays by your skin. Now the deep arteries, they're covered in a connective tissue layer, and you don't see them at all. So you don't see any of the blood in that. So the superficial arteries that you would see in here they match the tissue around it, so you don't see them. You see the superficial veins, which are a little bit deeper than the superficial arteries, and because of the filtering of the light, they appear blue. Okay. Again, trivia. You don't have to know that, but I thought it was curious. Also, if you ever have a chance to go to Philadelphia, they have a science museum, kind of like the Cleveland Science Museum here. It's called the Franklin Institute in Philadelphia. If you've ever been there, you know what I'm talking about. It's pretty cool. If you're traveling through Philly and you want something to do, I suggest you go spend a day there. It's really neat, especially if you like anatomy. They have an entire wing dedicated to anatomy. They have a 2-story heart you can go walk through, which is kind of cool.
Really?
Yeah. I mean, it's not a real heart, obviously, but it has staircases. A whale heart, gets close to that size, but it has a staircase that goes through. You can walk through the different chambers, and it's pretty fun. But probably the neatest thing they had there was they had a display of different animals' blood. Okay, now all vertebrates have red blood, but then it gets really wild. Things like sea squirts and grasshoppers, and they had. I wish I could remember which one was which, but they had purple blood, yellow blood, orange blood. You have a lot of different colors. Yeah, and I was very surprised. I did not know that. There are a lot of different colors of blood out there. So some of these different animals have different pigments in their blood. Okay, so that was neat all by itself.
Is it like a survival? Do you know why?
It probably just has to do with what their coordinating metal ion is. It's not all iron. So some different metal ions have different colors. So your blue blood probably has something like copper in it. All right. Now, this slide deals with some terminology that I'm really going to let go mostly until we talk about respiration. But the idea of forming oxyhemoglobin is called loading. Okay, forming oxyhemoglobin, that's called loading. And then forming deoxyhemoglobin is called unloading. So you'd want to load the hemoglobin in the lungs, and you want to unload it in the tissues. For now, that's all I'm going to say about that. When we get to respiration, we're going to talk about the partial pressures of the gases in the blood and how it affects this. Okay. Now you carry 95% of your oxygen. You carry it bound to hemoglobin. All the oxygen that you bring in, almost all of it, is bound to hemoglobin. Relatively little of your carbon dioxide is, however. Okay, only about 20%. And actually, I've seen that number usually more like 15%, is bound to hemoglobin. So the majority of your oxygen is bound to hemoglobin. However, the minority of carbon dioxide is. There are a couple of reasons for that. And again, I'll get into that more when we do respiration. But for now, I'll just say, we take the carbon dioxide and we turn it into a polyatomic ion called bicarbonate instead. We complex it with water, and then we turn it into bicarbonate, and we carry it that way. And red blood cells are crucial for doing that. They contain an enzyme. Red blood cells contain an enzyme called carbonic anhydrase. red blood cells contain an enzyme called carbonic anhydrase. I need to say CA. Carbonic anhydrase is one of the fastest enzymes we've ever discovered. It's very, very fast in its action. And it can, for our intents and purposes, pretty much instantaneously convert carbon dioxide to carbonic acid, which then breaks down to bicarbonate. And that's why red blood cells have carbonic anhydrase, is to convert carbon dioxide to bicarbonate. And then the bicarbonate is mostly pushed back out into the blood or carried in the red blood cells. So most of your carbon dioxide is actually transported in the blood in the form of bicarbonate ion. And red blood cells contain the enzyme carbonic anhydrase, which facilitates that conversion.
Is that all one word?
Carbonic anhydrase?
Yes.
No, it's 2 words. Carbonic anhydrase.
Sum that up just one more time.
So carbonic anhydrase converts converts carbon dioxide to bicarbonate. Converts carbon dioxide to bicarbonate.
Where is the carbon dioxide bound to hemoglobin?
To the globin chains.
Globin chains?
Yeah, out here.
Okay.
So when carbon dioxide actually does bind to hemoglobin, it binds to the globin chain, not to the heme center. And I mentioned something about that last time we spoke, something significant about that. There's metabolic poison that we all have to be concerned with in our lives called carbon monoxide. Okay, instead of CO2, it's CO. Carbon monoxide, as it turns out, does bind to iron.